I'm Jen Leisure with the Quilt, and I appreciate all of you joining us. Welcome to the third seminar in our Quilt Campus Cyber Infrastructure Seminar Series for our Quilt members and their institution partners. We are recording today's session, and as you've all come in on mute, I'd like to request, if possible, for you to turn on your video so we can see everyone's faces, and also if you'd be willing to put your organization in your name in the Zoom, you can do that by clicking on the upper right corner of your window there and hit rename. That way we have an idea of who's on the call with us and who we're talking to in our conversation today. I'd like to go ahead and start with a couple of introductions. First, I'd like to introduce Wendy Huntoon, who is a consultant for the Quilt working with us to support this series of seminars. Wendy is known for her work to enhance high-performance networking infrastructure, technology, and services for the research community. She is a past executive director of Kimber, which was a statewide research and education network in Pennsylvania. Prior to Kimber, Wendy served in a number of roles in our national community, focusing on enhancing research cyber infrastructure. And we're grateful to have her with us today. I'm also very pleased to announce our facilitator and our presenter for today's seminar, Jason Zurawski from ESnet. Jason is a science engagement engineer at ESnet in the science engagement group, where he works with members of the research community to identify the role of networking in scientific workflows and identify and suggest recommendations to improve those workflows. Jason is co-PI on the NSF-funded Engagement and Performance Operations Center program, or EPIC. He's co-PI along with Jen Schoep from Indiana University. And so many of us in this community already know Jason, so I always feel funny, Jason, in introducing you, because I always feel like everybody knows your background already, but we're very grateful for your expertise and your time today in leading the session. Wendy, I'd like to turn it over to you for a few minutes here before we get started.
Sure, thanks, Jen. And Jason, thanks to you and your team for providing the seminar today. This seminar, entitled Identifying Campus Cyber Infrastructure Needs, is really focused on some of the more technical aspects of the CC STAR solicitation. One of the things that we've seen in the past with how to prepare an infrastructure proposal, it often talks about identifying the science drivers or some of the actual sort of proposal writing fundamentals, but it doesn't go into the actual technical aspects at all. So the seminar today is aimed at doing that. It's going to be a little bit more of a survey. There's definitely going to be some in-depth technical information. There are a lot of slides, and the materials will be available afterwards. And so we do have 90 minutes. And there's going to be time for questions and answers. As we go along, if you have questions, type them in the chat window, and Ken Miller from ESnet will probably answer some of them on the fly, and the ones he can't answer, when Jason pauses either during the talk or at the end, we'll ask those questions as well. So Jason, I'll turn it over to you.
And thanks, Wendy, and thanks, Jen, for that great introduction. So first of all, is my audio coming through okay?
Loud and clear.
Okay, now let's make sure this all works. And hopefully that is everybody seeing the slides.
Looks good.
But we're not seeing you, Jason.
Well, we have to make a choice today. It's either good audio or good video, but it is not going to be both, because we have a lot of people sharing my connection today, and they're all playing video games. So, you know, that you're only going to get to hear me instead of seeing me. But that's a motivation. So when we are able to go back and have conferences, you'll get to see me there. So this talk is based on a lot of material that's been developed by lots of people besides myself. Ken and Eli are going to pop in for portions to help answer questions. But the goal here is that I want to go through sort of a breadth level of understanding for a lot of the things that you need to know as you prepare the CC STAR solicitation. In the couple of times that it's been offered, and hopefully when it's offered again in the future. So I'll give some introduction to that. I'll talk a little bit about the solution space, which is a couple of different technology components that you sort of knit together to make a good solution. and then sort of putting it all together using the technology and the sociology aspects to have hopefully a successful approach at this. And then the other thing that I'll add here is that please, if something is not clear, ask in the chat room. Ken will try to answer them live. Otherwise, Jen will stop me and we can have that conversation. I think it's better if the questions come as I'm doing this versus trying to do them all at the end. So just as a reminder, if people are not familiar with it, the last round of the solicitation is still online and public. You can go and look at it at that URL right there. But the overall goal of this program was to try to get technology support for the research community and install this at the campus layer where a lot of this work needed to happen. And there's a lot of good and investment that this program has done in the approximately 8 years that it's been around. The last time that I looked, and I think that this is dated to a couple of months ago, there was about 250 awards. I believe 49 states and jurisdictions have been a recipient at this point. $150 million, give or take, and about 130 of those were campus network upgrades. Others were research projects and similar things. And a lot of the awards from this last round are still trickling out. I know a couple of people have gotten their announcement already, and there's probably still a few more that are due in the next couple of weeks and months. What is this really meant to do, though? You know, build CI, of course, is what the outcome is really going on here. But what we want is we want to be able to improve scientific outcomes in some measurable way. And this is what our group focuses on, is to try to understand how to link together the different scientific and research activities that populate a different campus environment and how they can utilize this technology to their fullest potential. There's a lot of things to consider here, and it isn't just the technology pieces. It's really how it's all going to plug in together, and it's more than just the physical aspects of that. It's understanding what the users really need to be successful in the jobs that they're trying to do, making sure that they're satisfied, and that's not the same as having the IT people be satisfied. We need to make sure that we're pulling both audiences here. And then also being able to measure the results and see if you need to make any changes going forward. Odds are you're not going to build it right the first time, and that's okay. We need to be afraid to fail in some cases because that's the only way that we're going to learn from our mistakes. So this content is going to be sort of going back to the core of this program and talking about the high level, these are the things you should be focusing in on. And not everything here is going to be technology focused. A lot of it is going to be sociology focused. And I'll make sure I try to hit on those different topics as we go through. So one thing that a past ESnet director, Greg Bell, was very fond of was this slide. And because of that, I try to include it in all my presentations going forward, is that we don't want to view network as just infrastructure. Network is, in many ways, just as important of a piece of the instrument as the scientific instrument itself. And what do I mean by that? We don't do science all in a single room anymore. We're going to be utilizing instruments and facilities that are located around the country, around the world, to accomplish all the different components of this. It may be people that are physically separated. It may be storage and computation that's physically separated. It may be analysis centers or other components of this entire mixture. And we need this instrument, this network, to be a part of it. It's the backplane. And because it's the backplane, we need to treat it like it was a scientific instrument. We need to have a firm understanding of how it needs to connect up all these different components, and we need a way to measure and ensure that it's acting the way that we would expect it to when we interact with people. So it isn't just the connectivity, it's usability. And this is where that social aspect really comes into play for this entire thing. So as we go through this, you know, you can boil this down to the 6 or so questions that you typically ask in these scenarios, you know, the who, what, where, when, why, how. Who and why, I think, are the 2 most important questions that we're going to be using as we go into this. We need to know the users. We need to know the use cases. And all of those things put together are going to help us guide what the technology choices are going to be. What and how, we're going to answer those as well. But those are easy from a technology standpoint. You know, once we understand who the people are, why they're doing the things that they're doing, we get a better understanding of how to answer the technology components that need to go in there. So the common theme and the mindset that I'd like people to think about as I talk about these different technology components is that we're not attempting to build network architecture here. We are building data architecture. And the reason that I'm using the word data and not network is because there's a lot of different things here that sort of go above and below that network layer. The scientist doesn't interact with the network and know that they're interacting with a network. The scientist is going to interact with a portal system or a workflow manager or just an instrument itself. They want all that stuff to work, so they're not necessarily thinking about all the underlying gook that makes it happen. So we need to understand what that data pipeline really looks like. And once we have a firm understanding of what it looks like and how people interact with it, we can then get into the steps that are going to be used to do the creation, the usage, the transfer and sharing, and the curation of all that data that the person is going to be creating and working with. So we need to, whatever we create at the end, we want it to be usable, of course. You know, we don't want this to be some walled garden that is completely inaccessible to the people that are going to be on your campus infrastructure. You know, we want this to be something that anybody has the ability to try to use and to be successful on. It certainly, and most importantly, must be defensible. This is not something that's going to be the wild, wild west. We want this to be a strategic asset. We want it to be something that people understand is a little bit different than our enterprise networks. We want it to be scalable. In the beginning, you may not have many use cases. By the end, you may have several. And that sort of growing, you know, we refer to this as sort of rolling the snowball. We want to make sure that this infrastructure is able to grow as the people come and say, hey, I need to be able to do this scientific activity on top of it. And then lastly, we want this to be an institutional capability and a source of pride. You know, this is something that could be talked about as you're luring in new faculty. It could be something that you're talking about as you're trying to initiate new programs and things like that within the campus environment. Many schools that have a science DMZ infrastructure will make sure that that information is passed along to the different faculty components because, hey, this is going to make you more competitive as you attempt to go for more research dollars. So that with that introduction pushed forward, I'll just pause for a minute here if anybody has any questions, and I also want to grab a drink of water. But the next thing that we're going to get into is talking about the down and dirty elements of the solution.
Any questions so far?
None in the chat.
Okay.
Okay. So let's talk about the solution space itself first, the users and the use cases. Our group, EPIC, does what we call scientific deep dives. And without going into too much detail, it's basically before we were not able to travel, we would parachute into a campus environment, usually working with our regional network partners. We did one of these with Learn, we did one with OrNet, we did one with Kimber over the years. Parachute in and physically talk to the people who are using the network. This may seem like a very foreign concept, but hey, they're the people that are actually doing the research. And we would ask a lot of questions. What are you doing? Why are you doing it? How are you doing it? Who are you interacting with? And by getting to the bottom of a lot of these use cases, we learned a couple of things. And maybe these are not very surprising, but users like a stable network. They want it to be up and available to do the things that they want to do, and they don't want to be surprised. They'd like it to be predictable. They want a low standard deviation from their expectations. So if they're expecting to be able to send data across the country to an Exceed center, they'd like that to work in a consistent and performant manner. And they want whatever is put in place to really fit with their process. And sometimes they're very scared of change and they don't want to have to learn a whole bunch of new technology. So it's important to have these conversations to sort of understand what these things are going to be doing. And then the last piece there is that if changes are going to be made, they want them to be done in such a way that it's not going to impact any of the three items above. So at the end of the day, they just want the thing to work and they want it to work well. The technology implementation and operations community sort of has a different and sometimes more destructive desire. It's, oh, we want to do new and improved things and we want to have value-added services and we think you know what you need, but we may not talk to you. And a lot of these are a little bit destructive. So you have to be careful when you go in and talk to these users. And the best way to figure out what they need is to talk to them and have those conversations. So I always like to throw in this cartoon into the talks that I give because I think it really encapsulates a lot of the experiences that we have. And I can remember sitting on a campus years ago where we were talking with both the technology purveyors and the scientists. And somebody mentioned the idea of perhaps installing a brand new SDN network and network function virtualization. And I thought that the scientist was just going to get up and walk out because they really don't care about those buzzwords and those terminologies. They just want the thing to work, and they want the thing to work well. So what does this all really mean? We need to meet in the middle. And by meeting in the middle, that means we don't have to understand all the technology, and we don't want the scientists to understand all the technology, and we don't have to understand down to the details of an atom about what they're doing with their science, but we need to be able to speak a common language. And this is sort of what the science engagement process means. It means going back, revisiting these things, trying to gain an understanding of what they're doing, whether it be just figuring out what the collaboration space looks like, or figuring out what instruments are being used and what the data volumes are going to be. And then that's going to help dictate how we craft the technology solution on top of it. There's a couple of things that sites get into the habit of doing that are sort of false starts. We've gone in and helped a bunch of people with their execution after they've received the money. We've also worked with a bunch of people craft their proposals to get there in the first place. But first and foremost is that science engagement step. We finally get into the technology now with that second item there, network infrastructure. And I think the biggest false start that we often get here is that there's a misunderstanding of the way that we should approach building our networks. And enterprise networking equipment is a lot different than what we need to be putting in place for scientific and research support. And we'll get into some detail on this, but basically it comes down to understanding what the wide area flows are going to be looking like and treating that a little bit differently than we would with our local area flows. Computation, often we don't ask, or we don't think to ask, what sort of computation needs to happen here. If you're doing most of your science on a laptop, you know, that's one thing, but do you need access to a supercomputer center? Do you need to be using high throughput technologies? All these different things are often not explored until it's well late into the process. And knowing that this is something that needs to be supported is important, because it helps us craft the right solution at the end. Storage, I think, is another problem that's going to bite a lot of us in the coming years here, because we have a mixture of available cloud storage, and we're starting to get into the habit of not having a lot of local storage as a result of that. Scientific workflows don't necessarily translate well to using cloud storage, and expecting somebody to use it without having that conversation beforehand could add a lot of pain and strife to what they're attempting to do. Using cloud storage means we have to have additional latency and time built into our experiments. If we had the local stuff available, we can often do things faster and facilitate things like sharing a lot easier. So it's just something that needs to be discussed. And then lastly, collaborating within the environment of the campus, talking with your research office a little bit more frequently. They're not just the mechanism to send in the grant, they're also the pipeline that tells you about who is going to be getting funding and where the upgrades need to occur. So speaking with them more frequently helps you get a better understanding of the people who need to have the support. And then lastly, ease of use. If I can't use the infrastructure, why are you building it? We often see this situation where the technology people build this thing in a vacuum, and then they cut the ribbon on it and they say, okay, everybody in and let's use it. And then months later, they're looking at the usage numbers and saying, well, nobody's using this thing that we built. And it may be because it's either too hard, not accessible, or just doesn't fit the needs of what the scientists asked for in the first place. So I'll do another little quick pause right here before we get into network architecture and design.
Please post any questions in the chat room if you have any. Otherwise, you can ask during these pauses.
Okay. So just a little bit of background on data movement. Like I said, we're designing a data architecture here. So now we're going to be mentioning words like data movement and TCP. And I don't mean to scare anybody, but we do need to use some of these terms. Data mobility and performance requirements for science are much different than what we would see in a traditional enterprise environment. Why is this complicated? It's complicated because a lot of the equipment and the protocols and the software and things like that are not crafted for what the research use case is going to be. It's sort of put right into the middle for the most part, because, you know, most home users don't need to have all this extra memory and computational power associated with just using a laptop to view email or websites. So because of that, the scientific community has gotten better at knowing that, okay, if I go out and buy a new server, if I go out and buy a new piece of networking gear, I'm going to need to do a little bit of modification to make it work well. Much like we see in the automotive space when people are tuning their hot rods on a weekend, right? This is the exact same thing that we're doing with our research networks. And what does this really mean? It means that we're going in and we're changing configurations, whether it be on the hosts themselves, whether it be on the ways that the network switches and routers are going to be behaving, whether it be the tools and policies that we put in place to make sure that we're being secure. It could also be using completely different data transfer tools than what we would see within the enterprise space. All of these things together are really just indications that we need to be careful as we design this thing going forward. So let's talk a little bit about TCP. This is the common protocol that a lot of stuff on the network uses. Mail uses it, web uses it, but also a lot of data transfer tools use it as well. And why do we see this so ubiquitous? It's because it's easy to program, right? The way that a programmer views the world with using TCP is that, okay, if I set up a socket pair on one end, I can throw information in and it just shows up on the other end. That's really easy. Because of that, we put a lot of emphasis on the ability of this protocol to work well. And TCP by design is meant to be a little bit more timid than some other protocols on the network would be. And what this basically means is that TCP is always sensing if something is going to be happening in the background. Let's say that we start to experience congestion somewhere because a pipe is filling up. This is actually a good thing. It's telling us, okay, this pipe is filling up. I'm going to send some feedback back to the two ends of this transfer and say, hey, I'm dropping packets. The network is busy right now. Maybe you should back off. And all other TCP applications that are sort of running across that same little segment will get that same signal. So everybody collectively backs off and congestion eases and things get back into a steady state. This is fine for something like web or email because they're small transfers. We probably don't even notice when this is happening. For something like a bulk data transfer, if we're sending lots and lots of data that's coming off of a telescope or a microscope or something like that, this backing off behavior is really destructive. It slows down our transfer. It makes things take a lot longer than it really should. So because of this, we have to be careful about how we design our networks. We want to make sure that they have enough capacity, but we also want to make sure that they're configured in such a way that they're not going to be imparting this congestion and packet loss behavior. So TCP is reliable. Whenever I say the word packet loss, it's not that we're losing the data forever, it's just being dropped. And odds are it's being dropped somewhere along the path, and we're not going to be able to detect where along the path it's being dropped. We just know that it has been, and we have to sort of recover from it. We're able to reliably do that recovery, but the tools that need to use this for high performance applications are going to suffer greatly because of this. The reliability mechanisms that are built in there really dramatically reduce performance. So a lot of the things that you're going to see with the Science DMZ design are that we're attempting to compensate for this. We're trying to build it bigger, we're trying to build it smarter, such that we don't ever get into a situation where we're going to be causing packet loss within our local environment, and that way our tools are going to perform really, really well. So this is a classic graph that we like to show, and I'll try to explain this as best as I can. I typically do a live example, but I didn't want to try to risk this on a webinar. You're looking at a couple of different plots on this. On the left-hand side there, the way you interpret that is that's the throughput. That's the performance in terms of megabits per second. So at the top, it's a 10 gig or so transfer. At the bottom, it's closer to 1 gig and below. On the bottom there, that's the round trip time in milliseconds. So basically, you're seeing a plot of performance as you get further and further away from these two different destinations. The purple line that's at the very top, this is the no loss situation. So in a no loss situation, if we were transferring data between something in a data center, 0 to 10 milliseconds, we would see performance in the 10 or 9 gig or so range if you were connected at 10 gig per second. And there wouldn't be any degradation because TCP is able to perform very well and the distances are small enough. Even as we go a little bit further out, let's say about 100 milliseconds or so away, you're going to see a natural degradation, and this is fine. This is because the protocol has to work a little bit harder to move the information across that distance, but it's not being reduced by packet loss or anything like that. The other lines that you see there, the red, the blue, and the green dotted line, those are all situations where we are experiencing packet loss. And in this case, it's 0.0046%. And that may seem like it's really small, and it is. It's about 1 out of 20,000 packets that are passing through the interface at any given point in time. You're not going to experience any pain, so to speak, if you're doing that within a data center. So let's say we're still within that 0 to 5 and maybe even 10 millisecond boundary there. You would still be experiencing speeds of maybe 5 gig per second or 4 gig per second. For most people, that's good. You know, their expectation is, okay, I'm still doing pretty well. As we get a little bit further out, past the edge of our regional network, as we go nationally and internationally, this is where you start to experience the pain. And that little tiny bit of packet loss, no matter where it is on the path, it could be local, it could be on the other end, it could be somewhere in the middle, it's going to be causing that degradation in performance. So the user is going to be experiencing less than a gig per second, you know, sometimes hundreds of megabits, sometimes kilobits for your larger international transfers. And this is where the frustration really sets in, because, hey, they just want to do their science. Something's broken on the network. They don't know who. They're going to come after you with pitchforks and flaming torches because, hey, you're the guy who built that network, right? So we need to make sure that we are designing these things such that, A, we don't have this happening if we can avoid it. We want things to work very cleanly. But B, we also want to be able to detect it if it is happening so that we can go in and try to fix it. So I'll just pause right there in case anybody has any questions on this. Nope. Okay.
Nope.
All right. So now that we've given you all the bad news, let's talk about the good news here. We can build stuff that gets around this. And one of the things that we're going to be doing here is we're going to be describing this in terms of performance-based approaches. We want to have there be dedicated infrastructure to support the scientific users. It could be shared with other use cases, but for the most part, we want it to be as clean as possible. And the best way to make it clean as possible is to separate out the business use cases from the science use cases. These are going to involve the installation and sort of configuration of well-intentioned data transfer hosts that are using modern tools, capable network devices, the high performance path. We want to have a more proactive model for looking at performance, and we also want to have the security posture be matched to what the science applications are meant to do. So what does that all mean? This is sort of the classic science DMZ in one slide here, and there's sort of 4 things you keep in mind as you're designing this. First and foremost, friction-free network path. We want those highly capable devices, wire speed, deep buffers. We'll get into a little bit of detail about that. If you're using virtual circuits, have that ability put in place. Most importantly, I would say, is the security policy and the enforcement must be specific to the science workflow. We understand the science well, and we want to craft the security to meet that. We just don't want to have a blanket security policy. We want it to be very tailored and very specific. We always like to say, locate this at or near the site perimeter, and I'll get into a little bit of detail about why that's a good idea. Dedicated machines that do the job of data movement, dedicated machines that do the job of performance and measurement and testing, and then of course that engagement with end users that we talked about. So that's all the text. It's better described as a picture as well though. And going back to something I noodled on a little bit earlier, we as networking people can build what we think is a perfect design. But you're always going to have users that try to get around what we put in place. And if we just talked to them in the beginning, maybe we would have crafted our design a little bit differently such that it was meeting their needs. So let's get into a little bit of detail about the architecture and design. There's many different ways you can do this, and some are more complicated than others. For the sake of this talk, I'm just starting with the bare minimum version of what the science DMZ is going to look like. I'm not going to go into any really intense examples, but if that's something that people want to explore, certainly send us mail, and we're happy to jump on the phone to talk about it a little bit more. The key point that we want to push forward here is that we want to eliminate the sources of packet loss and friction. So that's what these different patterns are really attempting to do. So first, I like to start with a bad example. The bad example is somebody got some money, they bought a new honkin' fancy server, and they're going to use this as their data transfer node. But they don't tell anybody about it. So they buy this thing and they stick it in their office underneath a desk somewhere, and they plug it in, and they have their Globus subscription, and they're attempting to move data to an Exceed supercomputer center. What's going to happen? What's the worst thing that can happen in this scenario? Well, this is what the network diagram may look like. At the bottom there, we have our DTN. It's high performance. It's meant to work at 10 or 40 gig. We plug it into our good old building or wiring closet switch on the floor of our office, and then we try to push data out to the outside world. What's going to happen? Well, first we're going to hit that first hop there, and that device may not be ready to accept 10 gigabits per second of data that's coming out. Maybe it doesn't have enough buffering, maybe it's overloaded and currently doing a lot of other things. Whatever the case may be, that's going to be our first source of packet loss and performance degradation. Then we have to cross our site and campus local area infrastructure, where we have a whole bunch of other stuff going on. We have mixed traffic coming in from printers and phones and HVAC and students with BYOD and all that other great stuff, and that's going to probably reduce our performance even more. Maybe we have a speed step down between 10 gig at 1 gig at some point. And then finally, we get to the outside world there via the firewall. So that flow that started as 10 gig per second probably isn't going to emerge our campus network much faster than maybe 1 or even less than that. We have the same argument in reverse if data was attempted to be downloaded. It's going to hit that perimeter firewall. It's going to be shaped a little bit. It's going to have to cross all the same campus local area networking. In either case, if you're pushing or pulling, you're going to experience a bunch of different problems that you may not be expecting, because all you wanted to do was plug in your device and hope that things work really, really well. So this is where that discussion with the user is very important. If we knew that they were going to be putting this DTN into the campus, we'd probably go over there and have this discussion. Does it need to be under your desk? Maybe I can put it in the high performance computing center. Are you sure you want to be running the software on that? Maybe you let me run the software and I'll give you an account. You know, all these different things can be hedged off at the pass if we just had that conversation to start. So how do we fix this? This is sort of the classic science DMZ example. And we used to say that it's a cartoon and nobody's network looks like this, but what we found is that a lot of people have designed their networks to look like this, and that's fine. This has all the basics that you really need to understand. So I'll go through sort of each piece here, starting with our DTN that we had in the previous example. This DTN is configured in such a way that it's going to have 2 paths that are available to it. It's going to have that clean, high bandwidth, wide area path that's represented by the green line. And then it's going to have the red path, which is sort of the site campus access to resources that may live locally. The goal here is that we're trying to split up wide area data transfers. We don't want them to originate from a laptop that lives over on the site or the campus side, because what we've seen is that if we try to do a data transfer from deep within the campus, we're going to hit a bunch of friction. So what we want to do is we want to have that originate from that DTN. The DTN has less hops that it has to deal with. It has the tools that are appropriate for trying to move the data across a long distance. And because of that, your attempt at trying to do wide area transfer is going to be successful. It has a lot less that can go wrong. How do we get information over to it? Well, in this example, we'd have to double hop it. We'd have to probably send it from our laptop or something like that that's within the enterprise side over to the DTN and then send it out to the outside world. In more sophisticated examples, maybe that DTN is plugged into institutional storage, or maybe it has a file system mount or something like that. Those are all enhancements that you can sort of add to this as you build it. But the key point here is that the wide area stuff has a fast path to get to the outside world. Now, is this machine just out there and exposed to the world? Absolutely not. We still must be thinking carefully about what security policy looks like. It doesn't have a firewall in front of it, but that does not mean that we're not protecting it. In this case, we want to have per service security policy that's applied directly onto that switch. It could also be applied onto the host itself. We know what ports need to be open. We know what peerings and hosts it needs to talk to. All of those things can be implemented within the device itself. It means a little bit more work to try to craft that security policy versus what we would get with a firewall. But because we know that this machine is only going to be running 1 or 2 tools, It's not running a web browser. It's not running mail. It's not doing all the stuff that would invite sort of malicious behavior. It's just running those data transfer tools. We can craft that policy and have it be rather stable and still be very performant. And then lastly, we also have our little persona node that sits off to the side that can help us with test and measurement. So this is the basic idea. I'll sort of pause right here in case anybody has any questions right now.
None in the chat.
Stunned silence. Okay. So a couple of design thoughts now that we've thrown out the basic idea here. Whenever we talk to different groups that are thinking about doing this, they sort of float two ideas to us. The first idea is much like our diagram. We're going to create an enclave. We're going to have it sort of be carved off of a border router, or perhaps we have it carved off of a network core somewhere, in either case. And then we slowly onboard the science use cases onto that dedicated infrastructure. This way is a little bit slower. It's a little bit more work because you do have to have those conversations, but it's mostly successful in the end because you know what needs to happen, you know how it needs to be designed, you know who's going to be onboarded and who's going to be using it. The other mechanism that people often float to us is a drop-in replacement for the entire network. Instead of making a special enclave, the idea is, okay, I'll just upgrade everything. All the campus devices, all of the building switches, all of those things will be upgraded to a higher capacity. And then somebody who's sitting in a lab across campus, they can just plug in and try to use this infrastructure. This is a little bit easier. You know, all we have to do is go in and replace things as we're going, and then hopefully that capability will just exist. There's some pros and cons to this, so let's kind of go through them. In terms of that first use case where we set up our enclave, the pros here are that you do gain that deeper understanding of the use cases, the traffic flows, the security needs, and those are all very, very important. For example, let's say that you have a biology user somewhere on campus that's experimenting with human subject matter. The data that they're working with probably has some health controls that are associated with it. Would you want to just expose them onto the outside world without putting proper protections for that data? Probably not. The other way you can think about this is that by having these conversations, you get out in front of that. You know, you don't want to end up on the front page of a newspaper somewhere. So by learning what these different use cases are and crafting the solution to support them, you're going to be in a better position going forward to do that. The secondary pro here is that you're able to build this to spec. And what that basically means is that you know what your growth pattern is going to be like for the next term of how often you're going to use this. You know, you design it for maybe 10 gig operation or 40 gig operation. Once the NSF grant is done, you still have this infrastructure in place. How are you going to upgrade it into the future? You need to understand who is going to be onboarded. You need to understand how much it's going to need to grow. This will help dictate if you need to put in place any chargeback models or things like that to sort of fund the infrastructure going forward. I think that this approach is easier to operate long term. My reasoning behind this is that there's fewer moving parts. Instead of me going in and having to replace 1,000 devices, I've replaced maybe 10. And because of that, there's fewer moving parts to go wrong. There's less configuration that I need to try to manage. And to start with, there's less users. It's not just a random iPhone or laptop that's going to connect to this. There is a very specific process that you need to then put in place to onboard people and understand what their use cases are going to be. As a result, I would say it's arguably cheaper to do it this way as well. Less stuff that you need to buy up front, less time that you need to try to configure and do all those different work. It is time consuming. This takes a lot longer and often you're going to need some help, but then again, that's why there's a lot of experts in this community that can help you with this. And it does require some dedicated staff to sort of handle this operation and onboarding. This isn't something that's just going to be completely plug and chug from an enterprise perspective where a user can come in and they see 2 network drops on their desk and they can just pick one and they're off to the races. There is a little bit more hand-holding that has to go into making sure that people understand why this infrastructure exists and the things that need to happen on top of it. In case of the second example here, which is the drop-in replacement, that is of course easier to design because, hey, you're just upgrading the entire chunk of the network with new stuff. everybody everywhere is now capable of that higher performance, but you don't actually verify that, right? We still may run into problems like we saw with that first DTN example where there's some friction somewhere and we don't quite understand where it may exist. I would claim that the security profile of this approach is much harder to defend. We don't know what's going to happen in this situation because really all we've done is supercharge our enterprise network. Somebody can be plugging in a laptop that comes with a bunch of malware installed on it. Somebody else could be just running Bitcoin mining on one of their computers across the fast network. There's a lot of bad things that can happen here. And in this case, this is why you have things like firewalls. Firewalls protect against the unknown. If we go about this in a methodical and very careful way, we can understand what all the different use cases are going to be and allow those and craft the security policy around them. Without knowing what those are, we have to protect against everything, and that's where we run into friction problems. It's probably going to be more expensive this way because, hey, we're replacing everything. And as a result of that, as the budget grows, there's probably an inclination to have smaller and less capable devices that are going to be in the path. So while they may be 10 gig capable, as you upgrade and add all these different things in there, they're probably not going to function at that level of performance. And then lastly, you have no visibility into who's doing what. You know, this becomes the Wild West when we run into this sort of setup here. Anybody can be on there, they can be doing anything, and you lose that exclusivity, that ability to treat this as a very special infrastructure that can be used for research.
We have one question.
Yep, go ahead.
All right, so how important is the buffer size when designing the DMZ? Cost of big buffers versus low-cost routers?
That is a great question, and I'm going to say give me 5 or so minutes and we will answer it.
Okay.
Any other questions right now?
Nope.
Okay. Okay, I don't even need 5 minutes. I need 2 minutes. In terms of equipment, the requirements for the DMZ are going to be different. It's not the same as just plucking a 48-port copper-capable switch that you would use to replace all the connectivity in a building. You don't need to have all the services, but at the same time, it needs to be able to do a couple of key things, and it needs to be able to do those couple of key things well. Really what it comes down to is the buffer question, right? We need to have deep enough buffers to support what those scientific use cases are going to be. And the questions that you always try to ask here is that, you know, you want it to be a clean architecture. So you want the single flow use case to go as fast as it possibly can. We want that to be wire speed. We don't want there to be any impacts of, you know, packet loss occurring within the device itself, because that's what causes TCP to be very upset. Because we don't need all this stuff, there's always this temptation to go cheap, right? You know, it only needs to be able to do a couple of things. And unfortunately, when we're talking deep buffer switches, the price does go up a little bit. What are we trying to protect against here? This is really the major thing that you experience as you're trying to pick out the switches and routers that must populate your network. We need to worry about all of the ingress and the egress flows of a device. So let's say we have a well-populated switch where we have a bunch of background traffic. You know, maybe it's connected at 10 gig, maybe it's connected at 1 gig. It's a bunch of chatty little machines. You know, sometimes they're doing web and email. Sometimes they may be doing data transfer as well. And then we have our bigger connected DTN that we plug into the same infrastructure. Now, that DTN isn't very chatty, but when it does talk, it talks, you know, at the 10 gig speed because, hey, if there's data to send, I'm going to send it at my wire rate. And I need to have that sort of up and available for probably multiple hours at a time if I'm doing a bulk data transfer or if I'm doing some form of data streaming. So what ends up happening within this switch at this time is that we have all this chatty background traffic that's consuming memory, and then we have our big bulk data movement that's coming in, and it's also trying to consume that memory. And once we run out, the switch is going to start dropping, and it does it in an indiscriminate way. You know, there just isn't enough sort of space on those output buffers to go to the outside world there, so we start to drop everybody's packets. The little chatty things are able to recover from that rather quickly because they're probably not doing 10 gig flows, but that 10 gig DTN is really going to suffer as a result of that. So we're trying to design the infrastructure so that it can accept these big use cases, and this is where we need to have the big buffers. Deep interface queues, therefore, are very important, and typically this means buffer. You have to be careful in some of the literature. Every vendor has sort of a different word for their output queue. You know, sometimes it's called virtual output queue, you know, all those different things. That really doesn't matter in the grand scheme of things. We need to know what that raw memory availability is, because that's how TCP sees the world. TCP is going to need that space to be able to send its information as it's going across. And I have a little bit of a math calculation in a second here that'll help you as you judge these things. The other thing that I haven't mentioned yet, but it's also good to know, is that we want these devices to have good counters and good telemetry that's associated with them, because if they're not performing as they should, we need to be able to prove that and go back and try to address that situation. So we want single flow performance to be wire speed as close as possible. So like I said, under-buffered network devices are pretty much the single greatest threat that we see. People sometimes get into the habit of just treating a switch as a port expander. You know, oh, okay, I need to have another device put into the path, therefore here, let me use a 24 or 48 port switch, and because of that, I can then get connectivity. This is where we often see the problems, because that sort of top of rack switch does not have the buffering capability to be able to do the work that we need for this bulk data movement use case. As you're shopping, you're sometimes steered into these non-optimal choices. That's why it's important to read the specifications, and even if you don't understand what the specifications are saying, ask for a tester so that you can try to verify it on your own and in your own environment. The other thing, and we'll get into this a little bit later, is the security devices are also a bit of a threat here. They have small buffers, but they also take processing time to do the job that they're attempting to do, which is why we typically say that the firewall is a poor fit for this environment. Yes, it does the job that it's designed to do, but at the same time, it does it in a less than performant way. So what does the inside of a switch look like? This is a really rough diagram, but basically you have a bunch of inputs, you have a bunch of outputs, and you have a routing function that sort of sits in the middle. Data is going to be arriving from these multiple sources. The buffers have a finite amount of space. Sometimes it's shared. Sometimes all of the buffers may be using one memory pool. Other times each interface may have a little bit of a memory pool. Regardless of that, it's limited. And because it's limited, and when it fills up, it's going to get into that behavior of dropping the data when it has no other place to go. The processing engine on the inside is what pulls off the packets and sort of does all the traffic management as we're going through there. There's always a delay that's associated with this. And one of the common observations that people make is they say, if I buy this big buffered switch, am I going to impart delay into how my video conferencing and things like that work? Yes, you will. You have a lot more buffer. You've thus added a little bit more latency into the path, and that may make interactive video a little bit more challenging. Go back to what we said a little bit earlier. If we've segregated off the science use cases off to the side, typically they're going to be able to function in this environment really, really well. We don't necessarily want to be mixing these with these enterprise use cases of video transmission and web and email because, hey, they have different requirements. So this is one more argument not to do the forklift upgrade of your entire network and to sort of build the science DMZ off to the side with these specialized requirements. So here's that math problem I was talking about. How much buffer do we really need? This is a calculation that's called the bandwidth delay product. And what this basically means, just ignore all the numbers with the fancy commas for a second, is that if I am going to be sending information in a stream, let's say a 10 gigabit per second stream across the country, 100 milliseconds or so from Seattle to Washington, maybe a little bit less than that, we need to have a certain amount of memory that's available at each hop. TCP works as a store and forward protocol, thus it's going to send a bunch of information, it's going to wait for feedback, and then it's going to send a bunch more. So what this basically means is that to get that expectation of 10 gigabits per second, we do all the bits and bytes conversion, and I need to have 125 megabytes of buffer available. And I need that available at every single hop. If I do not have that available at any of the hops along the path, that is where we start to experience the packet loss and congestive situation. And TCP will back itself off as a result of that. So this is where we start to become bottleneck engineers. We need to understand if there is going to be some bottleneck in our path. We don't want this to be in our local area network. We certainly don't want it to be in our regional and our backbone networks as well. If we can guarantee that there's enough space for this, it all works well. If we ever get into a situation where we have less than that, it does not work very well. So let's go back to those little tiny top of rack devices that we mentioned a little bit earlier. You know, buffering is not important on the LAN, and this is because you have less latency. So if I still wanted to get 10 gigabits per second in my data center, rack to rack, or even host to host, it's 1 millisecond of latency. Therefore, I only need about 1.25 megabytes of buffering available. And this is why those little cut through and low latency switches are desirable for a data center, but they're really, really bad for when we're trying to do a wide area transfer. So this is why we want to design our network to support this. Now, the question, I'll turn it around a little bit, that somebody asked is, you know, yes, there's some cost that's associated with this. I don't need to go out and buy the biggest honking router for every single hop in my network. You know, I don't need to be using something that ESnet or Internet 2 would be using for their backbone network at every single stage of my campus network. Really, all I need to do is isolate my DTMs, have them so that they have a clean bandwidth path to the outside world, maybe going through 1 or 2 of these big devices, and we're good. We don't need to go in and redesign the entire building network. We don't need to redesign the entire core. Really, we just need to make sure that that path from the data transfer node to the outside world is as big and as clean as possible. That should reduce our costs significantly. When we get into the habit, or when we get into the situation of trying to upgrade everything, that's where the cost is going to balloon. So I'll just pause right there to A, see if I answered that question, and B, see if anybody has any others.
Yeah, I think the question's answered. It's a question about, you know, is Epic open to reviews, like proposed designs, equipment specs, and I replied yes there. And then I just mentioned if there's anything around traffic size, the number of transfers, including source and destination, that helps to determine buffer size and transfers.
Epic is always happy to do reviews. In fact, we've done about 10 in the last 2 months, so send them our way. We like doing that. So just a visual representation of what I was talking about here. This is sort of the behavior that you see with TCP. And the way that you interpret this graph, much like the other one, is that your throughput is on the left-hand side there, and time is sort of on the bottom there. The transfer is going to have a natural sawtooth pattern. It's going to sort of ebb and flow. The black bars represent congestive loss. So that's when we drop a bunch of packets and TCP has to back off. And in this situation, the little device that we were testing through just did not have enough buffering to support this flow as it was going through. And this is what you see when you try to do a wide area based transfer through a device that just can't handle it. And there really isn't a way around this. The only way around this is to throw money at the problem, and it's to make sure that you are sending your transfers through a device that's capable of supporting them. All right, let's talk a little bit about monitoring and measurement. Really, we want a way to be able to detect and hopefully fix if there's a problem on our wide area transfers. This starts in the local network, it extends into the regionals and into the backbones and into the other side as well. So we need visibility, and things happen. Stuff breaks, things get out of code, things become, you know, they're not as big as they used to be if they haven't been upgraded. So all of these things become a risk as we're attempting to do a wide area data transfer. Where do the problems typically exist? Well, they exist everywhere, right? If we're looking at any diagram that's trying to take us from a source to a destination, we could have intra-campus congestion, we could have congestion between domains, we could have a latency dependent problem like a switch with small buffers somewhere along the path. Because of the way that TCP performs, though, we get into this false diagnostic behavior where if I'm testing to something in my data center or maybe even in my regional network, I don't exercise TCP enough. Therefore, it's always going to show me quote unquote good results. So even though the problem is local to me, it exists over there on the destination side, I'm not going to experience that. And I'm going to blame somebody further out because, hey, my network is working fine, right? So we need to have visibility into what's going on here. And what that means is that we need to be able to detect what we call soft failures. A hard failure is easy to detect. If a link goes down or a device fails or we have a fiber cut or something like that, there's alarms and ways that we can kind of get an indication that something has happened. Soft failures really don't have that same sort of indication associated with them because if we read the TCP RFC from a couple of years ago, As long as TCP continues to function properly and the internet system hasn't become partitioned, you're not going to get that transmission error back to you as a user. So we need to be able to detect when these soft failures are happening, and the only way that you can do that is by observing them from the outside. That's where the perf sonar nodes come in. A lot of the diagrams that you'll see always have a little perf sonar node that's either right next to the DTN or right on the border device. And most campuses at this point have deployed them. I think the last time I looked at the directory service, there was around 3,000 or so nodes that are deployed worldwide, and that's incredibly helpful. What that basically means is that if I'm experiencing a problem between myself and an Exceed supercomputer center, I'm pretty much guaranteed to be able to find a perf sonar node along that path where I can bounce a test off of. And I can try to isolate what the problem is. If my throughput is working well to my regional and it's working well to the backbone network, but then it starts to degrade as I get into another end, into the destination network, I have a good indication that, okay, stuff is working well up to this point. Maybe the problem exists over here. And then I can work with the people that are located at those different sites to try to isolate and fix whatever problem may have come about. How do we do this? We do this with regular testing. The perf sonar software has the ability to set up these regular tests where we're doing a constant bandwidth ping or a latency ping, and we're able to sort of graph these results over time. And the goal here is that we want this end-to-end performance indication. We want to know if the performance between me and Exceed is regular and stable and doesn't fluctuate over time. We can add more tests as we have more collaborators. We can take them away. It's easy to configure these things. So how do you do this? You develop a test plan, and the test plan can be just adding a couple of regional destinations. It could be important collaborators. It could be major facilities like supercomputing facilities and instrument facilities, all those different things. And then once we have all of those things, we can visualize them into a graph or into a dashboard or something similar. So your typical site may have a couple of perf sonar nodes. ESnet has them at all of our different router locations. I know Internet2 has a number as well. A lot of regionals have them deployed. Ideally, we want to have one perhaps at our site border in front of our firewall. And then we also want to have one wherever our science is going to be happening so that we can get the same indication of what the user would experience if they were trying to do a data transfer. So what does this tell you? You know, this is just one example of many that we have. And this occurred on ESnet a couple of years ago. We had a slowly failing optic. You know, things happen like this. Optics get old, machinery breaks. And we would not have known that this was a problem unless we looked at the data over time. We're able to see that sort of slowly degrading performance as time went on. And then finally it triggered an alarm somewhere and we went in and repaired it. And by having this visibility constantly available, we can pinpoint when problems occur and where they're happening within our networks. So I'll pause right there if anybody has any questions about perf sonar.
No questions.
Okay. So now we've talked about the network pieces, we've talked about the measurement. Let's talk about data mobility. DTNs have been a concept since the beginning of the CC Star program. And a couple months ago, we sort of went through and we tried to figure out, you know, has this concept really evolved so much that we need to change our approach in how we talk about it? And the original idea has been there since the start, but the basic idea I think is still the same. It's a dedicated host just for the task of data movement. What do we mean by that? It means that that host is not doing anything else. It's not running our DNS server. It's not running mail. It doesn't have general logins so that somebody can check their mail or look at a Flash-based website. None of that stuff. It really has one function, and that function is to operate the data movement tool. Because it has that limited application set, we can put a pretty strict security policy on top of it, either on the host itself or on the switch it connects to, and be pretty happy with how it's going to be protected. You know, there's not going to be any risk of something bad happening because, hey, we know what the application is, we know what its behavior is, we know what our users are going to be looking like as they try to talk to this thing. We really do not want anything to impact the data channel. We, of course, want to protect the control channel and the management plane as much as possible. Usually the DTNs have 2 feet. 1 foot is going to be facing into the local area network. That could be an InfiniBand connection, maybe it's Ethernet, you know, whatever the case may be. We typically call that either the management or the control channel. And then it's going to have the wide area piece. That's going to be the piece that's facing the outside world that allows us to exchange information with our collaborators. And as you saw in our diagrams, we want this and the persona node to be in the DMZ enclave as close to the border as possible. In terms of the technology support, you know, technology has advanced. Processors are faster, memory is cheaper, all those different things. But the design is still pretty much the same here. You know, yes, it may have SSDs. Yes, it may have a slightly better CPU or a better operating system. But for the most part, it's still meant to be this dedicated machine that's tuned up to just do the active data movement. There's lots of different ways that you can approach the build itself. Often people send us questions related to DTNs because they just don't know where to get started. And this is a valid question to ask, right? I think the best way that you can think about this is that you want it to do that job and you want it to do that job very, very well. There's one sort of conflict here is that people think that they need to build the biggest DTN that they possibly can. And we would actually caution against that. Do you need to go out and build a 100 gig capable or a 400 gig capable DTN? I would argue no. And the reason that I would say that is because right now there is not a whole lot of science that requires 100 gigabit per second streaming capability. We're going to get there in a couple of years, but right now we're still dealing with either parallelism that gets us into the 40 or 100 gig range, or still 1 gig to 10 gig sort of flows that are going to be going between facilities. I think it's much more scalable that if you're going to get into the DTN game, you try to do multiple DTNs that are at the smaller speeds, you know, maybe multiple 10 gig capable ones versus one giant 100 gig capable one, mainly because you have a little bit more scalability options. Your dollar goes a little bit further if you're using more off the shelf hardware versus something that's cutting edge. The other thing that you always need to remember here is that these need to integrate with other workflow components, you know. These are going to have to integrate in with institutional storage, or they're going to need to integrate in with the tools that the users are using. Thus, you want them to be a little bit more general purpose than something that's just, you know, the biggest honkin' DTN that you can buy. What does this look like when we try to put it into practice here? You know, here's another sort of little cartoon of our network. We have our DMZ router. We have a bunch of DTNs. So in this case, we've scaled them horizontally. We have a bunch of 10 gig connected DTNs. And each of these is backed up to our institutional file system. Now you'll notice 2 things. First of all, the institutional file system is back behind our firewall. This is fine. This is actually very good. We want to protect that from the outside world as best as we possibly can. We're going to have a bunch of file system and security controls on that because, hey, that's the data. We need to protect the data as best as possible. The DTNs are going to have security controls associated with them too. You know, there's only going to be the ports that are open for that application and for that use case. And the users are going to be able to utilize them to send the data, but maybe they don't have shell access. And that's a good thing. You know, we don't necessarily need to give users full control over these things because, hey, they just need to use that application that's sending information. The DTNs are going to either push or pull from that institutional file system to the outside world. They're not going to have any friction as they try to do that. And equally, the file system is still protected against anything bad that can happen. We have logging, we have all the layers of protection that we would need to ensure data integrity in this case. So I'll just pause right there in case anybody has questions about this diagram.
Nothing so far.
Okay. Like we said a little bit earlier, what we're trying to do here is we're protecting against oversubscription. DTNs are bursty. Because they're bursty, they're not always talking, but there is going to be that bulk data movement that requires that line rate connectivity. So if I go back to that picture, that little Science DMZ switcher router that's right there, that has to have our big buffers. And equally, our border router hopefully should have some big buffers there. So if we're designing this, that is our wide area path of interest. That is the path that needs to be upgraded and supported to hit this wide area data movement use case. We don't have to upgrade anything on the enterprise side to support this. That's the other suggestion that we're making here is that if you can't do that, if you don't have the ability to sort of buy that Science DMZ switcher router there, the green one, you can home run your data transfer node directly to your border device. Be careful if you're doing this, of course, because that may institute some other things that may be a problem for you in the future. You certainly want to have that be protected and have enough security on it. But this is sort of a first step that you can do if you don't have the ability to upgrade things along the path all the way. In terms of storage architecture for the DTN, there's two approaches that you can do here. The first way is that it's sort of an island. This would mimic that first diagram that I showed a while ago of a DTN that just lives off on its own, right? It has local storage. It has an internal RAID. It's mostly self-contained. People have to send in data for it to be staged, and then they have to send it out. It only has the 1 foot there. This is probably the more common use case that people try to do, is they have them be 2-footed. And what this basically means is that it doesn't have a lot of local storage associated with it. It's going to have RAM to facilitate the data movement needs, but it doesn't have local spinning disk. It's connected up to the storage area network or a global file system in some way, and users can just treat this as a pass-through. They're able to initiate data transfers to the outside world and have it just come from wherever the institutional storage happens to be. So then we can get into a little bit more complicated example of how do we plug in other stuff to use this DTN. In this case, if you look on the right-hand side near the bottom there, we have an instrument network. So let's say we have a bunch of sequencers or microscopes or cryo-EM devices, whatever the case may be. We have things that create data. Ideally, we'd want to be able to write the data from those devices either to the DTN directly or to institutional storage. And a lot of these things may have a Windows PC that they have to talk to, because the Windows PC is what controls the software or the firmware that talks to the instrument. There's some tricks that you can do to sort of convince the Windows PC that it doesn't have a local disk anymore, and the DTN can be its local disk. So we end up just writing directly to that resource. That then facilitates any sharing that we need to accomplish. We also have the DTN then plugged into our storage area network, and we're able to send and receive information from it directly. This sort of setup is how we see a lot of larger instrument facilities adopting this sort of approach, right? They've outsourced the job of all data movement to a pool of machines. It doesn't have to just be one. And those machines are responsible for anything that's going to be sending, receiving, or basically manipulating the data in any way whatsoever. And then all the storage area stuff is sort of protected on the back end. In terms of hardware recommendations, we get this question a lot. So therefore, we just have a web page that talks about this. On that web page, there's 3 examples right now. The newest and greatest version that we have supports both 10, 40, and 100 gig operation. We purchased a bunch of these last fall, and we've been rolling them into production. In fact, I think Ken is going to talk about this tomorrow on the other webinar that we're doing. We're going to have a bunch of new machines that are deployed on ESnet very shortly for testing purposes, so people would be able to start using those. We also have the old specification for the 10 and 40 gig platform and our 100 gig platform that's used on the test bed. So let's talk a little bit about software. We've sort of solved the hardware layer now. Software really, really matters. And most of the performance problems that are reported to us revolve around the software question. It's, you know, somebody using an older protocol or an older tool to try to invoke data movement activities. What we find is that the best tools usually support a couple of different things. You know, there's the ability to do parallelism. They are a little bit more aggressive with regards to using the network resources that are available to them. They may have an API that allows for integration. What this really means is that you can't be using an older generation tool like SCP or FTP. You need to be using something like GridFTP or Aspera or any of those other high performance tools. So we ran these tests in 2005, and I have some updated results after this slide. But basically, back then, we were trying to do a test over a wide area connection. We were connected at 10 gig. The network was tuned, the host was tuned, everything was working as it should. But if you use a tool like SCP, you'll notice that our performance never got above 140 megabits per second. Why is that? It's because a tool like SCP is functionally unable to work at those high speeds. It has limitations that are built into the application itself that will ever allow it to go faster. So even though we have the fastest machine and the fastest networks available to us, we just weren't going to get it out of this application. If you applied a software patch called the high performance networking patch that Pittsburgh supercomputer developed, you got a little bit better. You got up to about 1 gigabit per second, but still you were nowhere near what you needed to be for high performance operation. FTP was very similar. Grid FTP, a tool that is designed to work in parallel parallel TCP streams, was able to get into the 6 or so gigabit per second range. And to get above that, you need to have extensive tuning on your disk and things like that. But for the most part, that's the dichotomy that's available between these tools. If you're using something that isn't designed for that application use case, it's just not going to work. So that was 15 years ago. Running this test even a couple of years ago, we're not much better with SCP operation. Yes, processors are faster, memory is cheaper and more plentiful, but it still is never going to get above that limitation that's built into the application itself. Really, you need to be looking at Grid FTP or FDT or Aspera or any of those different tools in a multi-stream sort of environment. This leads us to sort of the layer that the scientist is now going to be interacting with. So let's say that you've done all these other steps. You've put in place your network, you've put in place your DTN, you have Persona running in the background, and now you're ready to turn the keys over to your scientific user. And what are they going to do? They're going to try to download some data, perhaps from NCAR or from any of the supercomputer centers, and they're going to need to fetch this so that they can do some local operation on it. So, you know, we look at the results of trying to do these downloads, and the performance varies. And this can be a little bit frustrating for them as well. What does the scientist see? The scientist sees just the ability of needing to move this data on an end-to-end basis, usually through the application that they're most comfortable with, which is often a data portal. And they see this, and they may not be happy what the results are here, you know. What we've experienced and what we sort of know from working with a lot of people is that large-scale data-intensive science requires that we build some stuff on top of all that networking infrastructure to make sure that it's working well. So our colleague Eli Dart did another set of experiments between all these different supercomputing facilities to sort of gauge what the performance is between them. And it's a little bit hard to read those numbers, but for the most part, even though these are 100 gig backbones and typically 100 gig local area networks and 40 gig connected DTNs, we're still not up to snuff of being able to move things at line rate. This was in March of 2016, after numerous months of effort. In November of 2017 now, you can see what the results got to. It took approximately a year, a little bit more, of tuning, constant communication between all these different centers to make sure that things were configured the right way to get up to these levels of performance. So it is not easy. It is certainly not automatic to be able to get to these levels of expectation. We need to work at it. Data movement is really, really hard to get right. There's a lot of moving parts. So you certainly can build the network, you can put all the stuff in place, but you're going to spend a lot of time doing the tuning and working with people and trying to get everything up to snuff once it's all in place. So because of that, and this is what Ken is going to talk about more tomorrow for the people that can make that conversation, is we started this data mobility exhibition. And the goal here is that we wanted all the different sites that had deployed infrastructure, either through the CC Star program or not, to start testing. Run tests to each other, run tests to big computing facilities, and send us the results. Because what we want to understand is we don't want to berate anybody and yell at them for not doing it the correct way. We want to help them. We want to make sure that everything is working how you spent all your time and effort designing, and hopefully milk a little bit more performance out of it if we were able to do so. So the reality of what we've all done is that we've plugged all this stuff together, and we haven't done a large-scale test of how it all works together. So that's what the DME is attempting to do. It's attempting to do this large-scale test to figure out if I am able to send things from a campus to an Exceed center and have it work reliably and predictably and performant. So, you know, we can abstract all that out. What is that really? It's DMZs, it's DTNs. But all of these things are designed independently. And the only way that we can tell if they're working well together is to sort of do the testing. So I would encourage people, if they have time tomorrow, to attend Ken's talk. He's going to go over a little bit of the results of what we've seen in the past year. Because of the pandemic, we're going to extend this for another full year, so there's still time to test if you haven't done so. And anybody that wants additional help in trying to make things better, we support that, and we'll get on the phone with you and have a conversation about how to do that. That is the connection information and the time. I'll just leave that up for a second in case anybody wants to write that down. And I'll also pause in case there's questions right now.
So Jason, this is Marla. You know, this is all great stuff. You know, I was talking to Jen the other day. We're looking at another project, and you know, the scalability and the troubleshooting when things aren't working, and trying to automate that. And I mean, do you have any kind of just general comments about that?
Being able to
how's that for a vague question?
Well, yeah, it's vague, but let me repeat it and see if I got it. So basically, being able to automate the task of troubleshooting when something has gone wrong.
Yep.
Yep, that's a hard one. I started doing perf sonar in 2004 when I was a grad student, and I don't think we've ever answered that question. And it's not for lack of trying. It's just that there's way too many moving parts to be able to fully automate it. I think where we are right now is we finally hit ubiquity, where I can look in the perf sonar service and say, I need to run a test between, I don't know, Rice and NCAR, and I can find a node at Rice, NCAR, learn, front range gigapop, and be able to get some results out of each of them. I know that some researchers have attempted to do large scale automation of debugging. Prasad Kalyam at Missouri has been instrumental in doing some of that work. But right now, I don't think that there is such a way to just have an expert system spit out an answer. You know, I think that we're still a couple years away from that.
Thanks, Jason.
Yep, sorry I don't have a better answer for you. So why do we care about this? I care about it because I don't want it to have to answer questions like this anymore. I want this stuff just to work, right? We don't want there to be a wizard gap. We just want the tools to work. We want the tools to work well. And the big scientific communities are already making these investments. So now it's up to us as campus and regional and national engineers to try to do the same exact thing. So the last thing that I want to hit on with the data mobility piece is portals. And this comes out of one of our deep dives where I was talking to a researcher and they were still into the habit of using thumb drives to sort of sneaker net their data around. And I said, well, what would make this easier on you? And they said, well, I'd really like to be able to just send somebody a URL and then they can download the data. And I said, well, there's things that support that. You know, there's these scientific data portals. The problem with a lot of the scientific portals is that they were designed about 15 years ago. So they're dated in time to the technology of the day, which is, you know, a web server, some browse and search and data access, and they're not really made to plug directly into a DTN. So their architecture looks a little bit like this, where, you know, your access method still has to go through the enterprise network. What we want to see is something like this, where we're able to sort of put our DMZ to work. We still have our data movement path associated with the DTNs. And even though we're interacting with a web portal to do the search feature, we then want the transfer feature to go and use the fast path that's available to us. There are some obvious reasons to do this. We're dealing with megabytes and gigabytes and pretty soon terabytes and petabytes as our common unit of measurement. And there's lots of data objects. So there's many different upgrades in terms of instruments and data that's being created by these things. And to support that, we need technology that is able to deal with that. We can go out and retrofit and build portals to deal with this, but that's significant and it takes a lot of effort. So at least what we've done on the Epic side is that we've developed sort of a portal in a box. And what do I mean by that? It's we've taken the Globus Modern Research Data Portal that already exists today. We've packaged this in a little container. I believe it's a Docker container. And we're able to work with people to deploy this on their DTNs and expose research data. It is not completely plug and chug. It's not at the point where, like Perfsonar, you can just download it and have it work automatically. There's still a little bit of configuration and futzing that must go into this. But we're at the stage now where we're trying to send this out to the wider community and see if this is useful. Our goal here is that if we can make it easier to install a portal and expose research data, it's going to allow us to leverage these hardware upgrades that we've all made collectively, our DTNs, our DMZs, and simplify the act of data transfer between sites. So Ken will talk more about this tomorrow as well, but if anybody here is interested in trying to deploy this portal software, please let us know. All right, so we're almost at the end here, and I saved the most thorny issue for last, security and policy. I think that most of the questions that we get after the obvious ones of tell me what DMZ router or DTN device I should buy is how do I secure this thing? I'll start with the goal. The goal is that we want to disentangle our security policy from the enterprise network and the business network and the science network. Those are going to be two completely different things. Because of that, we're able to make a couple of assumptions here. The first assumption is that we don't want to get into trying to fix or modify that enterprise side at all. Leave the firewall there, leave the IDS and IPS there. Those are all fine. They're doing the things that they need to do. Over on the science side, the science data traffic is rather simple from a security perspective. In most cases, it's going to look like two things. It's going to be probably an encrypted control channel where we're going to be sending all the commands and stuff like that that we need for a tool like GridFTP to work. And then there's going to be a data channel. And what does the data channel look like? It's probably encrypted as well. But it's a bunch of ports that are opened whenever we need to send the data across. Data is going to flow across those, and then the ports are going to close off again on the other side. Maybe it looks like streaming instead of it being just a bulk data movement. The other thing is that if we've designed our DMZ correctly, we don't have a bunch of other stuff on there. We don't have building control systems. We don't have printers. We don't have phones. We don't have pretty much anything except for those data movement tools. Because of that, we can implement security controls just for that science stuff, and that separation allows us to optimize how well we can do that. So we like to view the DMZ as a security architecture as a result of that. We're able to segment these risks, and because we're able to segment them, we can have a more granular application of the controls that we're going to put on that stuff. We have a limited risk profile. We're able to apply the specific controls that we want to that data transfer host. So here's a really brief example. Let's say that we do have a common data transfer host that's used for any research data. Now I have somebody who's doing HIPAA or FERPA or some form of protected data research. We can create another set of security controls for that special DTN and have it still live in that same security enclave. We don't have to go in and change a whole lot of stuff because remember, we've segmented that off from the rest of our network. Now we can apply whatever security controls we need to that host and still have it meet all those specifications. We've removed a lot of degrees of freedom here, and that makes it easier to secure. It makes it easier to achieve that high performance that we're looking for. And most importantly, it's easier to troubleshoot. When something goes wrong, there's less moving parts. We're able to identify what's happening and hopefully put a fix in place. So the big myth that we often hear people repeat back to us is that, we designed this to avoid firewalls. Yes, in a way, we don't want to see firewalls in the path, but that does not make this less secure as a result of that. The reality here is that the science DMZ is about being performant and secure. If I've done my job correctly when I design this thing, I know what all the use cases are going to be. I know the users that are going to be populating this. Those users have an understanding of what I'm expecting of them, and they have an expectation of how I'm going to operate this. I can put in a bunch of different controls that are still just as valid and protection worthy as a firewall, except I don't have to worry about performance being a factor anymore. I know that it's going to perform well, and we're able to get that same level of security as a result of that. So think about how you would design any other piece of your network. Let's say the residence hall networks, the business application networks. All of those different things have different risk profiles, and they're all clearly different. That's the same idea we want to apply to this. Maybe you're already doing this in other pieces of your network, and if that's the case, then it's probably going to be easy for you to think about this mode. But that's the idea that we're trying to convey here, is that we want to follow the same concept from a security perspective. We want to design our controls and our mitigations and apply them just for that science traffic. So do we need to ignore security? Absolutely not. We still will be protecting our systems, but we want the security policies and mechanisms to be implemented in this sane and performant manner. So if not firewalls, then what? Well, we're going to put a bunch of different things onto here. You know, first and foremost, it may be ACLs and things like that that are going to be protecting the hosts, maybe at the switch level, maybe at the host level itself. We can still use an intrusion detection system as long as it's not impacting any of the traffic as we're going to go in here. We want to enhance the utility of the science infrastructure. That's something that you should always try to keep in the back of your mind. So I'll just pause right here while everybody has a little bit of a break and reads a good Dilbert. There we go. I'll use Jen's chuckle as indication that everybody's finished reading it.
The networking people are just happy that there's now firewalls so we can blame.
There you go. So what does it look like when we try to send high performance traffic through a firewall? Well, it looks crappy. This is an old example that I did years ago with Conan Moore at University of Colorado. And he said, hey, I'm having trouble with trying to do a transfer with my physics people. And I said, okay, let's put some persona measurement on that. And we looked at it, and at the top is the direction that had to go through the firewall. You know, one direction it was okay. The other direction it was just really, really bad, you know, 50 kilobits or something a second. And then, you know, the direction that didn't have to go through the firewall was good in both directions. So yes, the firewall was impacting about 20 times slower than the non-firewall use case. And how did we get around this? Well, you know, we A, upgraded the firewall, but B, also tried to move off the data movement tools from behind the firewall such that they still had the same levels of protection and were not exposed, but still protected and able to do the things that they needed to do. So the big finish here, I've thrown a lot at you today. I want to leave with sort of the last social concepts that you're going to need to remember as you go into this. None of this works unless you talk to people. Everybody who's involved in this, from the operators of the network to the users of the network to the administrators who are writing the checks, everybody has to be bought into this. This is usually a very different and often disruptive way of thinking about how to design a network. It goes against a lot of the things that we're taught as we're getting our trainings and going through school, because we're doing something a little bit different, right? We're not designing this like we would design an enterprise environment. The security people need to be on board. All the other strategic people that are involved in this process need to be on board. At the end of the day, you're going to develop a strategic asset, and everybody has to understand what the purpose of that asset is, how to defend it, how to protect it, how to upgrade it, how to operate it. You know, all of these things mean that you need to have conversations, and it isn't the conversation that you're going to have as the check is being cut after you got the award. You need to start a lot earlier in the process to make sure people understand what's going to be going about and how you're going to implement it. A part of that is sensible usage policy. And I didn't start with this because I didn't want to scare anybody, but you need to start thinking about this. What is a sensible usage policy? It means that the people who are going to be using this thing need to understand how to use it and how to onboard things, and that they're going to be sort of expected to behave in a certain way. Equally, you as an operator need to be able to understand the services that you're going to deliver to these people. You know, the use cases are very important in trying to craft what the usage policy is going to look like. And like we've said since the beginning, all of this revolves around data mobility. And what does that mean? I either need research data and I'm going to do something with it. Maybe I'm going to analyze it. Maybe I'm going to hold on to it forever. Whatever the case may be, I need to understand what that data mobility use case is. And I need to be able to point back to it as I'm designing these things for those users. So what do you need to do after it's put in place, or preferably before it's put in place? You need to have a conversation about access methods. The DTN is probably the way that you're going to be sending information in or out. You want to avoid trying to use people's laptops. You want to use the correct tools. You want to make sure that the people who need accounts are going to be getting accounts. We have a little bit of a write-up that's available there. It does not cover everything, but it's a good start. You also need to define an AUP, and this is basically who and what can, should, and will be sent across this infrastructure. You know, what happens when something bad happens? If somebody's account gets compromised or somebody is using it to send information that they shouldn't be, there needs to be a policy that's spelled out about what's going to happen and how to deal with that. We also have a usage policy. It's not complete, but it has a lot of information. And lastly, define what the monitoring and measurement and security expectations are going to be. This may mean, you know, if somebody wants to put their machine on the network, maybe you don't want them administering it, because how are you sure that they're going to keep the host up to date? They're going to keep the security and the accounts up to date. This may be something that the IT organization wants to start doing for the users. Maybe you're running the DTNs for them and you're just giving them accounts versus them just putting their research machines into the network. Above all else, be transparent. Keep those lines of conversation open. So, summary, know your users, know the use cases. You are designing a data architecture because you need to be able to support both the ingress and the egress flows of the information. There's going to be a lot of decisions that are thrown at you with regards to the networking gear, the data transfer software, hardware, the measurement, the monitoring, all those different things. There's lots of help out there. We're here to help. People on the Quilt list are here to help. Any question that you have, somebody has probably asked it before. We'd love to be able to answer them again. You want to facilitate usage because remember, you're building this for people to use. You know, the worst thing in the world is to build an infrastructure and have nobody use it. So make sure that you're facilitating that, and then have a good story for what the long term is going to look like. Usage, onboarding, expansion, maintenance, all those different things. So last thing that I'll leave you with is that this is what we want to see the world look like at the end of the day. We want there to be this science networking infrastructure that lives at the bottom layer. We want there to be DTNs, and we want there to be a data platform, because at the end of the day, that's what we're all using this for. We're using this for data exchange. So I will leave it on this screen right now, and I will take a drink of water, and I will wait if there are any questions.
So Jason, we do have a question, and in the chat room here, can you please address how curriculum needs for large data sets fit into that ecosystem?
So I'm guessing that what you mean by that is educational opportunities for students that may be trying to download or retrieve different data sets. Is that what that means?
Yes, if a faculty member wants to use the students to access large data sets.
Okay. So I'll answer this question by way of an example. We worked with a very small school in Wendy's old neck of the woods last year, the year before. It was more of a teaching school than a research school. And the use case that they gave to us was we have a bunch of biology and computer science students that are taking a bioinformatics class. And as a part of that, they're using an infrastructure called Galaxy. And they would regularly sort of download data, run the Galaxy software on their laptops or on lab computers to do the processing. And then, you know, at the end of the day, they'd have results they would end up sharing back with it. The way that we sort of designed this infrastructure, it didn't facilitate that we wanted to be able to plug the DMZ directly into all of their laptops, but we left it at, you know, there would be sort of one dedicated pathway where people could download the master data set and leave it locally. And then all of the students in the lab environment or in their laptops would then be able to hit that local resource. So at least the way that it was designed is that we didn't want everybody going out and grabbing the wide area copy, but using that to facilitate the local use case. That was a little bit more secure, and that made everybody feel a little bit more comfortable in how it was designed. It did take working with that researcher to say, hey, can we do it this way though? And at the end of the day, they agreed, yep, that's a little bit better. So I guess the answer is sociology. You need to talk with people and make sure that everybody understands, yes, we do have this capability, but let's figure out the best way to use it.
Okay, thank you.
Are there any other questions? All right. Well, a big thank you to Jason for today. You packed a lot into a short amount of time, and we appreciate your ability to do that and providing the resources with the slides along the way too. So, thanks also to Jen Shope, Epic, and Ken and Eli for being here and supporting this as well. And we're very grateful to have resources like Epic to help with your specific examples. If you need some assistance, they are there to point you in the right direction. We'll be continuing our seminar series. Let's see, it's not next Thursday, and in the next following week, it will be Tuesday, August 25th is the seminar number 4 in our series at 3 Eastern, and we'll be reviewing putting together campus and regional cyber infrastructure plans. So we hope you can join us then. A recording for this webinar and slides will be available after, so we'll be following up with you with that. Thanks again, everyone. Thank you, Jason.